Everybody. Well, I want to welcome everybody to this special colloquium. This is the Adler Colloquium, and I can't think of a better person to give the Adler Colloquia than Chandralekha Singh. She is it's particularly fitting because her research is in physics education, and Andre Adler's passion was physics education, and he taught the practicum and was following closely the literature in physics education and science education. So Chandralekha is a distinguished professor and the director of the discipline-based science education research at the University of Pittsburgh. She has many, many accolades. She's a fellow of the American Association of Physics Teachers. She's a fellow of the American Physical Society. She's won teaching awards several times at the University of Pittsburgh. And she recently received the APS, that's the 2022 Dwight Nicholson Medal for Outreach. And this is a medal that recognizes the humanitarian aspects of physics and physicists created through public lectures and public media, teaching, research, or science-related activities. And the citation is for work in broadening access to physics through research into removing barriers to success to the field faced by marginalized groups and how to overcome them, and addressing those challenges directly through meaningful research-based action. I know her well personally, and also through her many, many public articles, that is articles in kind of in the APS News, in Nature, in Scientific America, where she summarizes her research. And I've enjoyed reading many of those, particularly equating physics with tennis. I liked that article a lot. So if you can get past if you could be a good tennis player, maybe you can be a good physicist. But I'm excited to hear about your work. And the title of her colloquium is Facilitating Thinking and Learning in and Beyond the Physics Classrooms using research-based approaches. So welcome.
Thank you so much, Andy. I really appreciate that introduction, and I'm delighted to be here. And so I would actually like to say to anybody, if you want to ask a question, you can do that as we go along, or you can wait till the end. Either way is fine with me. So I'm going to give you a couple of examples of the kinds of research studies that I have done in physics education. And so the first one that I want to talk about is one that focuses on what is the role of intuition in physics problem solving. So basically the question is, what does it mean to think like a physicist? We all, marvel at, the fact that physicists are so good at solving physics problems. And the question is, what is it that is special about us? Can we actually help our students learn the same skills that we have as physicists? So in order to understand that, you have to actually somehow put, say, physics faculty who are experts in physics in the same situation that students are in. Because what you're really doing is you're asking your students to solve problems in quizzes or exams that are not exactly the same problems that you've taught them, but they are some kind of transfer problem that use the same principles of physics. So the question is, can we find some problems like that professors are not really used to thinking about? And will that put them in the situation that students are normally in? In other words, will they have to think on their feet to solve those problems? So here I'm going to tell you about one of those problems that I found in introductory calculus-based book, Halliday-Resnick, that you probably are already familiar with. And so this is a problem of a spinning wheel. So the wheel spins, falls on the ground, slips for some time, and then starts to roll without slipping. And the question was, how does the final speed of the wheel, when it starts to roll without slipping, depend upon the frictional coefficient on the surface? So if the kinetic coefficient of friction is increased, will the final speed at which the wheel starts to roll without slipping be more, less, or will it not make a difference? So this is the question. So, and we asked this question to 20 physics faculty in interview situation, and we asked this to many introductory physics students across like 14 different universities, like 2,000 students. And some students were also interviewed individually about this. So what do you think is the answer to this question? Because this is one of those problems about which physics faculty don't have an intuition. Think about it for a second. It turns out that the correct answer is that the final speed at which the wheel starts to roll without slipping does not depend upon the frictional coefficient. And that is because there are two things that are important here. One is how much is the coefficient of friction? And the second thing is how long does it take for the wheel to lock in and start to roll without slipping? And they work in opposite directions. So if there's higher coefficient of friction, the wheel will lock in quickly and start to roll without slipping. And if it's smaller, then it will take a longer time. But the total amount of energy that is dissipated in the form of heat and other things will be the same. Now, notice that there are two ways to really solve this problem. You can use an elegant method, the conservation of angular momentum about the point where the wheel first touches the ground. And since the angular momentum is conserved about that point, the final speed should not depend upon the frictional coefficient. On the other hand, you can also use equations of kinematics for linear and rotational motion, and then finally equate the two, and you'll see that the frictional coefficient drops out. So the final speed shouldn't depend upon the coefficient of friction. Now, faculty had a really difficult time solving this problem. So basically, notice this was an interview situation in which this was given on a piece of, on a sheet of paper, and they had to read it and they had to solve it on their feet without having thought about it before. And even though this is a problem from the textbook, this is one of those problems that faculty don't usually assign to their students. So they haven't really thought about it. So they had to do the thinking on their feet. And oftentimes, people focused only on one thing or the other, like either friction or how much time it takes to roll without slipping. But one of the things that was very clear was that if they were given sufficient time, they would have solved the problem. So like, for example, they were still using good problem-solving heuristics. What do I mean by that? For example, they were doing conceptual analysis of the problem. They were saying, let me think about what's given, where I'm going, what principles of physics would I be using? Can I use conservation of energy, momentum? Some people even thought about angular momentum, but notice that that is a tricky thing because you have to think about the point about which angular momentum is conserved. Some people, people were also drawing analogies with familiar situations, which is a really good thing. Like, for example, what happens to the wheels of an airplane when it actually, lands? How would the coefficient of friction determine the final speed at which it starts to roll without slipping? This is a great heuristic for problem solving. Similarly, people were actually thinking about limiting cases. What happens when there's infinite friction or when there is like no friction at all? It may not help in this case because if there's no friction, then it'll never actually roll without slipping. But these are still good heuristics that we should be teaching our students, something that most of the students were not using on their own when we actually interviewed these students about the same problem. Now, the other problem that both faculty and students were given is this ballistic pendulum problem. So what is that problem? That is this one. You have two putties which are hanging on a ceiling. One of them is raised to a certain height. It goes down. The two things collide, stick together, and go to a certain height. The question is, how do you find the final height of the two things stuck together in terms of the initial height? What do you think? Do you think that faculty even took the time to think about reading the full question, or did they just blurt out the answer? Yeah, so I mean, for them, this was like, they didn't even look at the full thing. They're like, oh, you would use both of these, so it was really easy. But what we found, this is the data from 2,000 students from 14 different universities. And you can see that this is data after instruction, you can see that only 27% of the students said that you need to use both these principles as opposed to only one or the other, or either one or the other, but not both. So you can see that this is a very hard question for students. And it makes sense, because if you think about it, there are three temporally separated things. This thing is going down, you have to use conservation of mechanical energy. The two things collide, conservation of momentum, and then things going up, conservation of energy. You have to put together those three temporally separated things, and the initial of one is the final of the other one. And so it is not easy, but if we think about the difficulty of the problem from our perspective, as opposed to the perspective of our students, these kinds of things have become automatic, but they are not automatic for students. We found that students struggled equally with both of these problems, and students got the same score for both of these problems on average when they were given both problems in open-ended format. So in other words, when many faculty said, oh, the first problem about spinning wheel will be so much harder for my students, it was not even true for those people who thought that way. So in other words, they were thinking about the difficulty of the problem from their own perspective. They were saying, oh, this problem, I have even done it in class, but their students didn't do any better than any other students. So the point is that just because you cover something really fast doesn't really mean that students have really internalized and learned those concepts well, because we need to think about the difficulty of these problems from our students' perspective. So one thing that we learned is that faculty, while solving these problems, were actually using good problem-solving heuristics, like thinking about what is given, where we are going, doing some conceptual analysis, thinking about limiting cases, thinking about the principles of physics, thinking about drawing analogies, things that we should explicitly be teaching our students and rewarding them for. But the other thing that's really important is that we should really think about the difficulty of the problems from our students' perspective. We should put ourselves in their shoes. Okay, so now I'm going to talk about the second study. That first study was published in American Journal of Physics. This is in Physical Review, Physics Education Research, and there's several papers that we have written on reflection and problem solving. So problem solving is a learning opportunity. By that, I mean that if we actually struggle to solve a problem, we often actually think about, why is it that this problem is so difficult? What is it about my knowledge structure? How do I have to repair it? How do I have to reorganize it? How do I have to extend it in order for me to be able to solve these kinds of problems in the future? Unfortunately, without support and without any incentives, problem solving can be a missed learning opportunity. And by that, I mean, students may not learn from the mistakes that they might have made in problem solving unless you reward them for actually learning from their mistakes. So we have done this study in introductory physics, and these are papers that we wrote a long time ago in 2011 in Physical Review. There are two papers that talk about how, when we ask students to actually diagnose their mistakes in the quizzes before providing them with solutions, how those students did significantly better than a control group that was not asked to correct their mistakes and they were just given the solutions. So somehow making students productively struggle a second time, by asking, so in other words, asking students to open their books and notes and letting them correct their mistakes really help them solve similar problems in the future, that involve the same principles of physics. For example, conservation of energy and momentum, both of them together in the same problem. So here I'm going to show you data from a study that we did in upper level undergraduate quantum mechanics, which was very similar. We wanted to know, if you just give the solutions to the students, for the mistakes that they had made on, say, quizzes or exams, midterm exams, how would they actually do on later problems that were very similar? And will there be any difference if the students were asked to first correct their mistakes before you gave them the solution? And so, one thing that I wanted to show you is that, this is the comparison group where the students were not given the opportunity to correct their mistake. They were just, given their midterm exam, for example, back, and they were told, here is the solution, the correct solution. And the incentivized group is the group that was given incentives to correct their mistakes. They were told, you'll get 50% of your points back if you actually take this thing home, look at your books and notes. You shouldn't be consulting with other people, but just look at your books and notes and try to correct your thing and bring it back on Monday. And pre means how did the students do on those kinds of problems the first time? And it's been divided into how the students had done in terms of like their performance the first time, those who didn't do well, medium, high, and this is all of them together. And this is the same thing in the incentivized group. What you see is that their performance the first time around is very comparable for the two groups. And the post refers to how did the students who actually were just given the solution without asking them to actually struggle a second time with the problem versus who were asked to struggle with it. That's the incentivized group. How did they do? And what you can see is that there is a clear difference in the way that the students did future problem solving of the same type, when they were asked to correct their mistakes for the low group and for the medium group. You compare the 66 with 88 and 50 with 51 with 78. And you can see that students are doing much better. Of course, the students who had done well the first time, they are always doing well, so it doesn't really matter for them. But notice that asking students to correct their mistakes for certain points back is a really good heuristic for helping those students think through deeply who otherwise have not done well. Now, you might say, oh, but I gave them the solution. Why didn't they actually think about it? Like maybe students will not think about it because they don't think that those questions will actually come again, or they feel bad looking at their solutions because we asked them, why didn't you, we asked some of the students, like in interviews, why didn't they actually look at it? And they provided all kinds of responses. But the important thing here is that if you really want all of your students to do well, then just asking them to correct their mistakes for a small amount of points back is a really good thing. And by the way, the great thing is that the second time around, when students have their books and notes and they struggle a second time, that struggle turned out to be a very productive struggle, in the sense the second time around, students' responses were really good. More importantly, later on, when students were given similar kinds of questions on future exams, they actually did really well. So they were able to transfer that learning to that situation.
Chandralekha, I just want to understand the study. You mean you just gave back the exams just the usual way with points deducted and X's and stuff like that, the way you usually grade an exam, that is with...
Absolutely. So just like some circles, okay, there's something wrong here, there's something here, and they saw that they might have gotten 5/10 on a problem, but it was not told to them exactly what the mistake was. So they had to look at their books and notes and figure out what the mistakes were.
Yeah, I see. That's very interesting.
Yeah.
Like a graph.
Yeah, and you can see that it makes a huge difference to the students who are otherwise struggling. They really productively struggle with, what mistakes they had done. And with the incentive, they will do a lot better. And later they do a lot better too. So here, this performance is their later performance on similar problems.
Also, just to clarify, so the comparison group was given a solution, but the incentivized group was not given a solution?
Okay, so the incentivized group was first given their own solution back and told to correct their mistakes. Okay. So for example, you give it on Friday and you tell them to bring it back on Monday by correcting their mistakes in homework, in looking at their books and notes, but not consulting with anybody else. Whereas the comparison group was just given the correct answer along with their graded solution.
Okay, so the incentivized group was not given the correct answers.
No, sorry, they were given the correct answer, but only after they had corrected the mistake. Sorry, all groups had the correct answer, but these incentivized group was only given the correct answer after they had corrected their mistake. So all groups had correct answer. But there was a step in the middle that was asking students to productively struggle a second time around. All right, so now I want to move on to the thing that I have done a lot of work in, which is improving student learning of quantum physics. And, I've written like 70 papers in this area or more, actually. So if you are interested in student learning of quantum mechanics in different topics, you can go through some of the work that I've done. And so, you might think that students might not have as many difficulties in learning quantum physics like they do in, say, for example, classical mechanics, because there's a lot of research in that area about how students might get confused between momentum and force, or how they think that when an object is moving at a constant velocity, there must be a net force, or how a huge trailer truck must exert a larger force on smaller cars, things like that. But the point is that what we find is that even in quantum mechanics, students really struggle because of the fact that the quantum paradigm is very different from the classical paradigm, and even students who have developed a very robust understanding of classical mechanics, struggle to learn that new paradigm. That's why another thing that I've been really promoting very much lately is that we should actually be introducing quantum early, even in the high school level courses. So because if you learn two languages, like my mother tongue is Hindi, if I learn Hindi and English at the same time, it doesn't feel like these are so different in terms of like not being able to comprehend something or not being able to speak that language. You kind of learn it together. So if you introduce two paradigms at the same time when people are younger, I feel like it might be much better, because the quantum, and of course you have to keep getting more and more sophisticated as you go further on. All the work that I'm going to talk about here is in the context of upper level quantum mechanics course. So, as I said, the quantum paradigm is very different. People who are familiar with position and momentum, now are suddenly finding, no, these things are operators that act on states in Hilbert space, right? And and in Hilbert space, no one can hear you scream. and the point is that, so the measurement outcomes are not certain. You have certain random probabilities of getting different outcomes. These are very different, this is a very different way of thinking about things. So we wrote a paper a while ago with some collaborators on classifying what are the different difficulties that students have in learning quantum mechanics. And these are based upon studies that were conducted at 9 different universities with graduate students and upper level undergraduate students. So let me just give you some example. So one of the things that we asked students was, if suppose you have a quantum state, which might be like a linear superposition of ground state and first excited state. And, depending upon the instructor, they might have used different notations because they were teaching course with slightly different notations. But the point is they gave similar questions. And the point was, what's the probability of measuring different values of energy, right? You can see that 67% of the students from 9 different universities provided the correct response. The second part of the same question was asking about what is the expectation value of energy. And you can see that suddenly the response rate, the correctness response goes to 39%. Now, you might say, why is this? Because if this was part A and this was part B, they were supposed to be related. And as you might imagine, most students were not answering the second question as part 2 of this question. In other words, if you think about expectation value conceptually, it's the average of a large number of measurements on identically prepared systems. So if the probability of measuring energy E1 is 2/7 and probability of measuring E2 is 5/7 and everything else is 0, then the expectation value should be 2/7 times E1 plus 5/7 times E2. But the majority of students who provided the correct answer actually said, oh, the answer, this expectation value is integral of psi star H psi. And, some people forgot orthonormality. Some people forgot the limits of the integrals or the fact that there was an integral involved or something or the other. And ultimately, their correctness response was a lot lower. So one of the things that I want to say to anybody who teaches quantum mechanics is that we need to think very carefully about how we are really actually teaching quantum mechanics, because a lot of times we are really not emphasizing the conceptual aspects of quantum mechanics. And even though the quantum paradigm is very different from the classical paradigm, it has a very well-defined structure, just like the way that classical mechanics is. And if we really integrate the conceptual and quantitative aspects, students are likely to do a lot better. Okay, another question that we asked students from 9 different universities was, will the probability density depend upon time if your initial state is this state, linear superposition of ground state and first excited state? And notice that, again, 43% of the students provided the correct response, and majority of incorrect responses said, no, the probability density will not depend upon time because the time-dependent phase factor cancels out. And that is not true, because again, the time dependence of this, phi1 should be e to the power minus I e1 t over h bar. This is e to the power minus I e2 t over h bar. And when you find the probability density by taking the absolute square, there are cross terms that don't cancel. So this is not a stationary state or energy eigenstate. Unfortunately, a lot of times the way that quantum mechanics is also being taught, people are just focusing on like solving differential equations, like, okay, this is like infinite square world, this is harmonic oscillator, this is hydrogen atom, and this is, maybe whatever, Stern-Gerlach experiment or Larmor precession, but somehow it all goes off as though, like there is some H psi is equal to E psi equation that is being solved, as opposed to thinking about what happens if you're in a linear superposition of stationary state. And notice that these kinds of ideas are really important in, quantum information science and technology, quantum computing, quantum communication, quantum sensing, all of these things are really important, and we are really not emphasizing it, and we are just solving H psi is equal to E psi, and the questions on the exam ask those kinds of things, and students can actually solve those differential equations that anybody in a math course can do, but they don't necessarily actually think about all the stuff that is involved in quantum physics. So notice that here I'm only talking about superposition. We have done also some studies on entanglement and other things, and we see how difficult those concepts are too, but I'm not going to talk about it right now. But basically what we found is that regardless of which school, which university the students were in, they were having very similar difficulties. So in other words, maybe the percentages were a little bit different, but you can classify student difficulties in only a few categories, okay? So the question is, what can we do about it? Well, we can actually think about developing learning tools that are research-based. By research-based, I mean they go through systematic research on how students, what difficulties students are having, and how you can use those difficulties as a guide, as a resource to build learning tools. So basically, we use them as their difficulties as resources. Those things are explicitly brought out, and students have to explicitly think through these teaching learning sequences where they have to actually think about, oh, why is this not correct? And why should this be correct? And there are certain situations where they'll realize that there is some discrepancy between what they are thinking and what the correct answer is. So these are basically what we call guided inquiry-based learning sequences. Inquiry-based because students are actually thinking through these things on their own. And notice that this is supposed to be after you have already instructed them, say, for example, using lecture. So this is not the first time you introduce to them this concept. Also, this is basically making sure that it's building on students' prior knowledge. So that's what I mean by, being in the zone of proximal development. So in other words, we make sure that students actually can make sense of these questions that they are being asked, and they're actually helping them also keep track of what they are understanding and what their problems are, and then how that can be resolved. So they are being given scaffolding or guidance to resolve those issues. So there are lots of hints and feedback, and they bridge the gap between the quantitative and conceptual aspect of quantum mechanics. And there are also often computer-based visualization tools. And of course, they keep students actively engaged. Now, you can give students pretest, which is after your lectures. Then you can give them these quilts, what we call quantum interactive learning tutorials, or quilts. And then after students have worked on quilts, which is best done in class in small groups, but you can also give them these quilts as homework if you wish, if you don't have class time. And then post-test is supposed to be given after they have actually turned in the quilt, or they have actually worked on it in class, right? And I'll show you, like, for example, here are some things from the time development quilt. So students, in the pretest, after your traditional lecture, will be asked, is the probability density in this situation depend upon time when the quantum state is a linear superposition of ground and first excited state like this? And let's say that I showed you already that only 43% of the students provided the correct response, and the rest of them said that it won't, because the time dependent phase factor will cancel out. Then at that point, they're asked to actually check their prediction using computer simulation. And here I'm showing you the time-lapse picture of what happens in this situation, So this is vertical axis is psi star psi, this is X. And you can see at time t equal to 0, it looks like this, the probability density looks like this, then it looks like this after some time, and then after some time it's like this, etc. So students immediately see that, oh, if they predicted that the probability density should not depend upon time, there is a cognitive conflict. It's like, oh no, I was wrong. Why is it that the time-dependent phase factor doesn't cancel out? Because it looks like it's different. So then the rest of the quilt after the pretest actually helps students think through these ideas. It helps them understand why is it that Hamiltonian of the system is so central to issues related to time evolution, and why when you think about the time evolution, you have to think about, is it a stationary state or energy eigenstate, or is it not? If it's not a stationary state, then you need to think about writing it in terms of stationary linear superposition of stationary states, and then tack on the time-dependent phase factors to each of those terms, and you'll see that the probability density will depend upon time. They get to do this in lots of different contexts. Some of them might be in infinite square well concept or context or harmonic oscillator, so that students can see that the same ideas apply across many different contexts. And when you look at student performance on the post-test, for example, you can see on average, they do significantly better than how they had done on the pre-test after traditional instruction. Here I'm showing you how the students did on various pre-test and post-test after traditional instruction and after working on the quilt, and you can see that student performance is always a lot better after working on the quilt. And notice that some of these you can also give as homework, not necessarily in class, even though the best thing, of course, is to have them work in small groups of, say, 2-3 students in class on these quilts. So like Mach-Zehnder interferometer is one that they really like. Quantum ideas of quantum eraser and things like that, students really appreciate. Stern-Gerlach experiment quilt is a really nice one because using a two-state system, it can get so many foundational ideas about state preparation, time evolution, measurement, etc. through quantum key distribution. We just published this 2 years ago. This is the one that uses Bennett's non-orthogonal polarization states of light. And again, it's something that students really like. Right now, we are developing one using entanglement, quantum key distribution using entanglement. We are also developing a quilt on quantum basics of quantum computing. So again, if you are interested in any of these, like they're all available, most of them are available on Fizzboard, except for the one that are in preliminary stages of development. But if you are interested in any of those, please email me. We are also developing like these clicker question sequences, we call them peer instruction tools, based upon like the Eric Mazur's idea of like having lectures be integrated with these clicker questions or multiple choice questions. So again, these things are also very effective. And if you're interested, we have almost 500 such questions for a full year of upper level quantum mechanics course. And here I'm just showing you some data on how students, like who didn't use any clicker question, how they did. This is the score out of 10 on the horizontal axis, and this is the percentage of students. And you can see that those who didn't use the thing in the concepts, in the questions involving infinite square well, these students didn't do as well as the students who had used clicker question sequences in 2 different classes. So again, if you are interested in any of those, like you can find them on Fizzboard, or you can email me and I'll actually send you those things.
Can I ask you a quick question about the quilt?
Yeah, absolutely.
Do you give the students the codes to do this modeling, or are that's something they actually develop? Say, you showed that the evolution of the probability density. Is that something they code themselves, or are they given some module which allows them to see that?
So notice that in most of the quilts, they don't have to do any coding. At the most, they might have to actually just plug in some numbers, so they might have to just say, okay, I will put, what is the coefficient of this or what is the coefficient of this, and the rest has already been done for them. And so then they can see what happens in that situation. So all of those predictions, but you can potentially actually, if your course also involves more computation, there's nothing wrong in asking students to also say code in Python or something, but these things are already pretty much coded for them, except maybe finding writing that state that they have been given in which they're putting some coefficients in. Does that make sense?
Yeah, that makes sense. I just wonder if they worry if that's like a black box for them, or if they understand what's going into the calculation of the,
Yeah, so that is a really great point. And since one of the things about all of these things is that time is very limited in the classroom. So how much time you're going to actually use for various things, will depend upon the instructor. So I feel like, if you really wanted them to code this thing, that's fine. That's perfectly fine thing to do. But within the quilts, when they actually open the simulation, the only thing that they have to do is plug in, some of these coefficients for various cases to figure out what that quantum state would be for which they are trying to predict what should happen. But yeah, absolutely. Feel free to actually let the students do the coding if your class actually has some coding experience for students, and students already know how to code in some language, some programming language.
I have a question.
Please.
How different are the pre-tests from the post-tests versus the quilt?
So I think that you should take a look, but they are not that different. So in other words, but one of the things that we have found is that, even if you just give pre-test and then post-test and there is nothing else in the middle, students do not do very well on those things. So they're not like, very, very far transfer questions. So, they're not identical, but they are actually kind of similar ideas. So if something is about, like, let's say X component of spin, the other one might be Y component of spin or something of that sort. If this thing is about some kind of a linear superposition here, that might be another linear superposition. If this is about some kind of like non-stationary state for infinite square well, like say, for example, A times X times A minus X, this might be like more like sine cubed X. That sort of a thing, but it's basically like very matched otherwise. Okay, so now I'm going to switch gears and talk about my work, my research on diversity, equity, and inclusion, and so I'm going to talk about how to improve students' self-efficacy, sense of belonging, and intelligence mindset in introductory physics. So first of all, I want to actually define the word self-efficacy, which is students' beliefs about their ability to succeed in a particular task, course, or subject area. And research has shown that it can impact students' persistence and engagement, and it can also affect students' performance even after you control for their prior knowledge and skills. And it can impact also how much time students spend on tasks, because if you're really stressed about something, you might want to not do that thing. And it can also impact the effectiveness with which students engage with learning. Because research shows that, anybody's brain, has working memory that can only keep 5 to 9 slots. And if somebody is really anxious about learning physics, they don't think that, they are good at it, they might actually get so worked up that some of their working memory resources could be taken up by anxiety. And so that robs them of some of their cognitive resources when they're trying to actually solve problems or when they're trying to learn. And that is not a good thing, right? So it can actually put student in a feedback loop, negative feedback loop. So that's a very bad thing. And if you think about the discipline of physics, right, this is the picture that has been shown a lot. But one of the things that you see about this picture that, it's not like, oh my gosh, I see all the founders of quantum physics, the first quantum revolution's founders here. But the other thing is, it's, there's only one woman here, Marie Curie, and everybody in this picture is white. So, I mean, like people who don't look like these pictures might actually look at this and say, do I have any, future in physics? Do I belong in physics? And, if people struggle, they might worry about these things even more. I mean, this one is a picture from a more recent conference in physics, and you can see physics, just like computer science and electrical engineering, these are some of the disciplines in which the representation of people who have traditionally been marginalized has not really changed that much. Right now we have 20% women at the undergrad level, 20% women at the graduate level, and racial ethnic minority students are even more limited. So I'm going to show you some research studies that we have conducted. So this is a research that we did in introductory physics 1 and 2, which is mostly for engineers and physics majors, okay? So what I'm trying to show on the vertical axis is self-efficacy, which is students' beliefs about how good they are in solving physics problem. And this is actually measured using a Likert scale. I think I'm really good at solving physics problems. You ask students at the end of the course to rate themselves on strongly agree to strongly disagree scale, you ask them these kinds of questions. This is at the end of physics 1, this is at the end of physics 2. These courses are mandatory for all the students in these courses. As I said, 70% of them are engineers, the rest are physics majors and chemistry majors. And what you can see is that the thing that strikes me at least is that women who have A grade have the same self-efficacy as men who have B grade at the end of physics 1, and it becomes worse at the end of physics 2. And in fact, there is no statistically significant difference between women who have A grade and men who have C grade in terms of their self-efficacy. Now, I must say that it's not just how well you're doing in terms of grades that matters, it's also your self-efficacy, how good you think you are in that discipline, how good you are in physics. So self-efficacy matters regardless of your performance, but it's really bad that after instruction, at the end of one full year of instruction, women's self-efficacy is, becoming the same as men's self-efficacy with C. If they are getting A, this is like self-efficacy with men with C grade. And in fact, these are some of the things that women are saying. I have pretty low self-confidence when I see how other people are so smart. Other people understand more than I do. For physics, I feel like I don't connect things. I don't feel comfortable in this class. It gives me a sinking feeling. I mean, on and on. But here, I'm going to show you more data from my own research. And here, I'm going to show you the vertical axis here is the mean GPA. This is the mean GPA, and this is the mean STEM GPA. You can just focus on this one if you like, because the trends are very similar in both. This purple thing here is shows women who completed their undergraduate degree in computer science and engineering. This is men who completed their degree in computer science and engineering. This is women who dropped computer science and engineering, and this is men who dropped computer science and engineering. So their GPA versus the year that this is their different years, what was their performance in different years, right? And what you see is that women who complete computer science and engineering have a higher GPA than men who complete. These numbers are like the number of people in that category. What you see is that the most shocking thing is not that women have a higher GPA than men do in these disciplines, but the fact that women are dropping out with significantly higher GPA in every semester. If you look at like this fourth year, women who are dropping out have the same GPA as men who are actually completing the degree. And if you say, oh, this is related to their self-efficacy and other things, what can I do if they want to drop out and go into a non-STEM discipline? It's not my fault. Yeah, it is our fault. There is something about the culture of physics that these people are actually dropping out. You don't have to be like, women don't have role models. They are always questioning whether they have what it takes to excel. Nobody is recognizing them. So it's not a surprise that they are actually dropping out. So this is from computer science and engineering. Let me show you the stuff from physics. So here is the thing from physics. This is actually math and physical science. So in order to have like large N, we have math and physical science. And again, you see similar trends. This is women who are actually dropping, and this is men who are dropping. And you can see that there's a huge difference in their GPAs. And these two are kind of similar, the men who complete and women who drop out. So this is not a good situation. Why are these women actually dropping out? And I must say that, if you look at like, if you do interviews with these people, you also hear stories about what are the kinds of things that they are going through. So let me also show you what is the situation in terms of physics.
I have a question about the last slide.
Please.
I mean, I guess the difference looks a little bit larger when using just the STEM GPAs than overall GPAs, which I'd imagine the STEM GPA would have more of a determination of if they would drop out than the overall GPAs, right? Particularly because if they have a higher overall GPA than their STEM GPA, then that would make them more encouraged to want to do a non-STEM field, right?
That is true that, I mean, this one has a higher GPA than this one does, but, the differential is more. And I must say that these kinds of differences themselves are really important. I can actually talk to you about this issue itself for 1 hour because there are a lot of things that I want to say about it. Let me leave you with just one anecdote. So Eileen Pollock, who was the first woman to major in physics at Yale University in the 70s, she wrote her memoir in 2016 called The Only Woman in the Room. I don't know if you read it or not, but the thing is, she writes about how she did really well in her courses. And she said that, undergraduate thesis was mandatory. So she did it on a theoretical thing. And she said, when I solved that problem that the professor has assigned to me, I ran to his office triumphantly thinking he was going to tell me, Eileen, you've done such a great job. You should go to grad school. And so she said, when she knocked on his door, he just said, okay. And he went back to his work. And she said, this lack of recognition, was so demoralizing to her that she went from feeling triumphant to feeling like she was at the bottom of the ocean. And she said, I still felt like asking him, should I actually do you think I'm capable of going to grad school? But then she said, no, why should I ask him? Because, if he didn't tell me himself, then, I'm not good enough. So this kind of recognition, lack of recognition is a big deal. And what she said is that she actually right now is an English professor at University of Michigan, Ann Arbor. And she said, I always actually did well in English and people always praised me. So I thought, let me do my grad school there. The interesting thing is physics is her first love. And so she went back to Yale when she was writing this memoir because she misses not being a physicist. And this time that professor was still there. And so she was much smarter 30 years later. And she's like, can I have breakfast with you? And he's like, of course. And so she then asked him point back, what did you think about my thesis, undergraduate thesis? And he said, oh, Eileen, not that many people do theoretical work. I must say, I still remember it. I must say your thing was like exceptional. And she said, really? She said, I got teary-eyed and I said, is it really? Why didn't you tell me then? Then I would have been a physicist. I miss not being a physicist. Do you ever praise anybody? Do you ever tell them that they're doing a great job? Do you ever actually tell them to go to grad school? And he's like, no, grad school is so hard. I don't want to give students the wrong impression. The point is, if you are not validating your students, if you're not recognizing your students, if you're not telling them that they're doing a fine job, students from the marginalized backgrounds, like women or racial ethnic minority students, people who don't have role models, they are the ones who are even more likely to exit than other students. Although recognizing and validating and praising students is a good thing for all students, so we need to be doing it much more. Also, like people who give 40% average in their courses, notice that if you're teaching for the first time and your averages are 40% in your course or 30% in your course or even 50% in your course, you can be forgiven. But the point is that, generally your averages should be more like 70% or 80%, something of that sort, because otherwise it's showing that you haven't really actually formatively assessed your students and you don't have any understanding of how much they know or don't know about something. Because you need to constantly, by formative assessment, I mean like things like clicker question or things like tutorials, those things are always giving you feedback on what your students have understood or not understood. Otherwise, you can think that students have understood when they haven't. And also, even if you're scaling people up in the end and giving X number of A's and B's, those 40% averages can be very demoralizing for students. Like they're like, okay, I have failed this course. In the end, the professor gave me a B+. But really, I didn't understand any physics because I kept getting like 50%, So I'm just saying that you need to also, think very carefully about how you are evaluating students. We also find, and I've done a lot of research on it, but I'm not going to spend too much time because I haven't, these are not parts of my slide. We have also seen that women do a lot better on low stakes exams than on high stakes exams, because, In high stakes exam, when, like your final exam is counting for 50% of your grade, the anxiety of the marginalized students is even more than all other students. They're like, oh my gosh, if you gave like a ballerina problem in the class, where this was an angular momentum conservation about why putting her arms close to herself was making her spin faster. And in the exam, you said, oh, a neutron star is rotating slowly, it's collapsing under its own gravitational force. What happens when its radius goes from this to this? Students are like, oh my gosh, this is not an astrophysics question. Why did you give me that in a mechanics course, right? No, it's not funny, because we need to think about how to actually help students transfer their learning from one situation to the other, because that's why physics is difficult. People get hung up on the surface features because we haven't really helped them think about the deep features of the problem and help them think about like the same thing in many different contexts. Or what happens when you dive from a diving board, when you put your arms close to yourself, will you actually make more somersaults or less somersaults? Like these are all angular momentum problems, but the point, conservation problems. But the point is, if we don't give students opportunities to do this, students start freaking out in the exam. And the ones from the marginalized group, they start thinking that they are the only ones who are actually having these kinds of issues. And they go into this kind of like anxiety mode where their brain freezes, they cannot think further, and they perform poorly. So the point is that what I'm saying is that what you said was absolutely correct. And there are many reasons here as to, why students are not doing. And yeah, if they're doing better in English compared to physics, and those things could be reason for students to actually drop out too. But the point is that we are not even creating a culture where we validate students and we recognize students. Here I'm showing you like what is the percent of students who drop out from different disciplines. This is bio, CS, engineering, math. And of course, this is our discipline, and it's the worst thing. 38% of the students who declare a physics major are dropping out. And if you look at the racial and ethnic minority students, it is really awful. Like 2/3 of the students in physics are dropping out after declaring a physics major. We should be thinking very carefully about what kind of culture we are actually producing, because a lot of times, we just don't do anything and we think, oh, if nobody encouraged me, nobody said anything, I still survive. Why should I encourage anybody else? Why should I say? No, those things are wrong, because especially it helps all students, but it's particularly important for women and racial and ethnic minority students. You can see that 2/3 of the people who declare a physics major actually drop out, which is a horrible thing, because these people declared physics major because they really wanted to be there. Also, like I'm not going to spend too much time on this because I want to show some of the things that have helped students. But the point is that if you look at like the level of marginalization, this is like no marginalization, first generation college student, low income students, racial ethnic minority students. This is first generation low income, first generation underrepresented, low income, underrepresented, first generation low income and underrepresented. You look at students' grades, like this is the first year GPA, right? The top one is women, the bottom one is men. You see a clear pattern that, we are not really supporting marginalized students, and the more, the higher level of like disadvantage they have, and it doesn't even matter which semester it is, like second year, third year, fourth year, like the trends are very similar. So that means that we are not really doing, because we need to be very intentional about supporting students who have traditionally been left out. So the question is, what can we do? So here I'm telling you one approach that can be a beginning thing. But in order to actually use this approach, I must also say that research is showing, and I can send you the paper if you're interested in, for example, this was a study that was done by Mary Murphy at Indiana University. And what she shows is that you yourself as a instructor of students needs to have a growth mindset about your students' potential. If you think that all of your students have the potential to do well in your physics course, then they will. But if you don't think, then they will not. So what they see is that if they actually gave faculty a survey in the beginning and asked them, do you expect only 30% of your students to do well, or do you expect that all of your students will do well? The faculty who said, my goal is to make sure all of my students do well, they saw that the difference between minority and majority students was much lower in those courses than the courses of the professors who said, oh, I think only 30% of the students belong in this class or something like that. Because, so in other words, those faculty had fixed mindset as opposed to the ones who actually were thinking that all students are coming with the prerequisites for this course. Yes, there will be some diversity in their preparation because different people have different privileges. They have gone to different types of schools, but I'm going to intentionally provide support to students who have traditionally been left out, and they make sure that all of their students do well. In those courses, they found that students actually had much less gap. By the way, this was a study done with 150 professors across different science disciplines with 10,000 students. So let me tell you about at least one way you can start. So, you know, these kinds of approaches have been used a lot in high school math courses, for example, by Carol Dweck and other people at Stanford University. You know, you might be familiar with Carol Dweck or Greg Walton and Claude Steele and David Yeager. These are people from Stanford, and now David Yeager is at UT Austin. They have done studies where they have actually looked at how does improving student belonging improve student performance, okay? And these interventions are very short. They take like 25 to 30 minutes at the beginning of the course. And the idea is to tell students that adversity is normal. Struggling is the normal part of learning anything. And in physics, even Einstein said, if you haven't struggled, you haven't tried to learn anything new. So the point is that, you know, this is really true. And so the idea here was to really normalize adversity and say to students that it's really about working hard, working smart, taking advantage of all the resources, you know, not succeeding at doing the problems, because failing is not really failing, but that's the stepping stone to getting to the next step and the next step. And so they should really feel proud of not getting something right away, and they should keep struggling with it. They should go to the TA for help. They should come to the instructor. They should actually work with each other. And they should be proud of telling other people that, yeah, they don't know this and they're struggling to learn it, because that's the way they'll get to the next step. And also telling students about your own adversities and telling them, yeah, when I was an undergrad student, I was struggling with those things too. By the way, Stanford has a really good site that you should go and check out. They call it the Resilience Project, in which a lot of faculty in different disciplines who are teaching there are telling about their own adversity. There's a person from physics who's saying, oh, you know, I actually got a C in my first physics course, you know, and here I am teaching you physics. So, and things like that, you know, like, so, but anyway, so in this particular thing, what we did is at the beginning of the semester, we divided 3 of the introductory physics courses that were taught by, that were really large, like 200 people. And by recitation, I mean those small classes with 40 students, which are problem-solving classes. So 6 of those recitations participated out of, you know, many recitations that were taught by these 3 professors, right? 3 professors classes. So, and the idea was to tell students struggling is the only way to learn something new. So they should be proud of struggling, since it means that they are on their way to learning something new. And they should be proud of doing challenging problems and not get it right away, because that's how you learn things. That's actually the path to being good at physics. And the idea was to reduce their anxiety, reduce their procrastination, increase their enthusiasm for solving challenging problems, and ensure that their limited cognitive resources, because I said your working memory is constrained by this 5 to 9 chunks, is used up for solving problems and learning physics as opposed to by anxiety. So I don't want to go through this whole thing because it looks like I'm running out of time, but I'll say that what we started out with is that, okay, physics department really wants to understand your concerns about being in this course. So why don't you tell me what your concerns about? Write it on the sheet of paper. And students wrote for some time. They wrote a lot. They were told to stop. And then we showed them some testimonials from students from prior years who had done really well, who had gotten A grades. And they were saying, yeah, you know, I was really concerned, but then I realized it was really about working hard, working smart, taking advantage of all the resources. And lo and behold, I saw that I did really well at the end when I started working with other people, when I started going to instructors' office hours and things like that. And slowly things started to click. And so, and then after this, students are asked to get together in small groups of 5 or 6 and discuss what they wrote on that sheet of paper. And why don't students realize that struggling is a good thing? And that's the only way that you can actually learn physics. And then after this, each group is asked to actually report out as to what they discussed. And what they find is that everybody is pretty much saying the same thing. And then after this, students, that is it, then the rest of the recitation is as normal, as usual. And what we find is that, first of all, after this thing, and if anybody is interested, I can send you the script for what we do, because now we do it in all of our classes, because not only did we find that women really said, oh, this was such a great activity that you did in the first week. Some students are like, who's in Tower B? Let's work together. We'll study together. Notice this is the beginning of the semester. But what we also found is that compared to the control group, in the social belonging group, where we were trying to improve students' belonging by normalizing adversity and having it be clear to students that actually it's a good thing to struggle. They should embrace it, because they should pat themselves on the back, because this is the stepping stone to learning physics. We find that there's no difference between the performance of men and women, whereas there is difference in the control group. And here you can see that the same kind of feature is also there by race. Even though the things are less statistically significant here than for the gender case. Also, this one of our colleagues in psychology, who's from the Stanford group, he came from there. He also did this intervention in biology in addition to helping us implement it. And in biology, again, what you see is that the differences by race were the ones that were eliminated when this intervention was done, because that's where the maximum advantage was. So you can see that these kinds of things actually help students the most who need this kind of intervention. So I would like to stop by actually telling you that when you're thinking about helping your students, you should think of it like that tennis, like being the coach of your students. And not only should you be thinking about your job as helping students become effective and efficient problem solvers and helping them develop a good knowledge structure of physics, but also strengthen their defenses by improving their sense of belonging, by improving their identity as somebody who can excel in physics, inculcating growth mindset, improving their self-efficacy, because when these things work, students will also become even more interested in doing physics. They will also have higher achievement goals. And overall, these two things interact with each other. So students will have less anxiety, they will feel less anxious. And these kinds of this approach where you are thinking of yourself as a coach for students that tries to create an equitable and inclusive learning environment where all students feel like they belong, and all students feel like they can actually struggle, fail, and failure is not really failure, but that's the stepping stone to getting somewhere. They are going to actually want to communicate with each other, and the relationship between the students will improve, and the relationship between the students and the instructor will improve. And ultimately, all students will benefit, but especially those from marginalized backgrounds. So I encourage you to use this kind of an approach. And if anybody needs a script, I can send you, because now we are doing TA training because we do this in all of our classes. So thank you so much. And I'll take any questions that you might have.
Thank you for a really excellent talk and lots of very practical things also that can be done. And I'm sure there are questions either online or here, but we have one here in this room.
Yeah, I was curious. So very early on in the presentation, one thing you mentioned was the importance of the instructors putting themselves in the students' shoes, right? Kind of understanding what the students are understanding, or like understanding what they're not understanding. And one thing I was wondering is, what are some specific ways in which people can do that? Because both as a student and as an instructor, I feel like that's been one of the hardest things, is when the teacher just does not understand where the students are failing to follow. Does that make sense?
Yeah, and that is an excellent question. And I would say that there are two approaches. Like, one thing is you can yourself give a pretest at the beginning of the class that relates to the kind of physics or math prerequisites that you might want to check in terms of what the students know or can do. The other thing that I would say now there is so much literature on, like I said, I have myself written like 70 papers on how to improve student learning of quantum mechanics and different things. And if you read those papers, you'll see what are the kinds of difficulties students have with, say, time development of wave function or quantum measurement, or for example, state preparation, or, what difficulties will they have in the context of Stern-Gerlach experiment or Larmor precession? And in introductory physics also, in many different contexts, like there are lots and lots of things. And the great thing is that, as I said in my own initial presentation, that when we did the studies in 9 different universities, like we don't find any difference in terms of the classifications of difficulties. What you will find is that maybe 50% of the students in one university have that difficulty, and it's only like 25% in another. But the classification for what are the kinds of difficulties they are having would be very similar. Similarly, the kinds of mathematical things that people are getting hung up on will be very similar. So in other words, and that is the good thing, because if 8 billion people on this planet had 8 billion different difficulties related to different topics in physics, you wouldn't actually know how to help your students. But the fact that student difficulties related to time development or measurement or something else can be classified only in 2 or 3 categories, and I can tell you that the most common difficulty will be this, then this, then this, then this. So like, for example, I know for a fact that if you ask students question about quantum measurement, a measurement related to, like, say, for example, something that was not energy, right? Some other thing. And if you say, okay, long time after this measurement, what happens to the state? Students will either say it will go back to the original state, or they'll say that the system is stuck in that state. Like, for example, if you do position measurement, like when the initial state was, say, first excited state, they'll say either, oh, it's stuck in that thing because it's a position eigenstate, or they'll say, oh, it will go back to the first excited state that it was in. And neither of these things is true, because the point is that your state evolves according to the time-dependent Schrodinger equation. So you need to think about how your state evolves. But based upon like research, I already know exactly what are going to be the 2 top difficulties that students will have about this. And then you can think about how to help your students with those topics. Do you see what I'm saying? So that's one way. Or if you really want to do it for your own student, keeping a day for pre-test for your own class at the beginning is not a bad thing, to get some general guideline for where the students are overall. And yes, everybody has prerequisite, but there is some diversity in student preparation. And if you're really wanting to help those students, all of your students, not just like the top 20, 30%, then, because notice that those students will do well no matter what. Really, you should be focusing on everybody else and making sure that the class is really valuable for all students. And also, if you make students actually, talk to each other through clicker questions and other things, the great thing about, and you don't even have to make clicker question. You can, if you think that that's too much work, then, you can actually even say, oh, what do people think about this? Here is a charge configuration. Do you think that I can use Gauss's law to find the electric field at any point here, or will it not work in this case? Because Gauss's law tells you about electric flux, but in order to find electric field from electric flux, you really need a high level of symmetry. So if you ask them about like some cubic charge distribution or something, students need to think, you can say, hey, can everybody talk to the person next to them and see like what happens in this situation? And then, you can ask some students, what are they thinking? The good thing is that all of the students have engaged in this. And notice that one of the things that my research has shown a lot in many different contexts, in upper level quantum mechanics, in graduate level courses, and in introductory courses, is that students, when they talk to each other, they actually not only just teach each other like what they know, they can co-construct knowledge. That means, what I didn't know and what you didn't know, we can actually figure things out. We find that roughly in 30% of the cases, students are co-constructing knowledge. They are on the verge of like being able to figure out, and 2 people who neither of them actually answered it correctly individually together figure it out right after that. So what I'm saying is that having students talk to each other, and also you have to realize that students who actually might know more than other students, they also benefit from this. So you don't have to worry about, oh, that will those 20, 30% of the students be bored? No, nobody is bored. And if you tell students and you frame it that way and you say to them, look, physics is giving you such a great background for future in terms of your personal growth, professional growth, and the kinds of things that I'm doing here are really going to help you because I'm really on your side. And because if you look at American Institute of Physics data or for any engineering data, what you will see, ABET data, problem-solving skills are something that employers value a lot, and physics is something that is helping them develop the general reasoning and problem-solving skills, how to be systematic in terms of making inferences about different things, but also they value your ability to talk to each other, ability to communicate ideas with people who know less or people who know more, and in this process develop some leadership skills. So telling students that these things that you're doing in your classes are really to help them, and it's going to really, in a low stakes way, help them communicate scientifically, make them better at developing, make them better at developing their leadership skills. I think that students are more likely to actually talk to each other and communicate. And as I said, if you're interested, I can show you, I can send you my papers where we show that even the students who knew the thing actually do better when they talk to other students than the students who actually, and it's not good only for the students who didn't know something. So all the students are benefiting from collaborating with other students.
Thank you. I think there's a question in the chat. Does the person who put it want to say the question, or should I just read it?
Oh, sorry. Do these ideas get any traction at the high school level? That seems to be where okay, so there definitely is work going on at the high school level. And this intervention that I talked to you about, believe it or not, these interventions have been going on for 20 years in high school math classes, and they have been found to be very effective. So I definitely want to say that there is, but again, high schools also have so much more bureaucracy. So while I totally agree with you that the earlier we can do something, the better it is, right? I mean, but unfortunately, high schools have a lot of politics, and they're very, very different scenarios in high schools. Some of the high schools don't have resources, some of them do, and we don't have any control over it. So while, yes, I mean, I feel like high school or even earlier, like middle school or even elementary school, can be a really good place to start. I think that it doesn't mean that we cannot start where we are, so that's what I want to focus on, because we are here in college and we can really shape our students' lives. By the way, I can actually send a video to Andy, which is from a colleague from Ohio State, Roland Kawakami. If you're in condensed matter, you might know him. Yes. Because he says that, using some small things in his class, has really changed the way that he teaches, and it has changed his life in terms of like his interaction with students and the interaction of one student with another student. So, even with small things that you do in your classes, you will see that the dynamic in your class can change significantly. And he is talking about, this is in a video that he's describing, like this is a condensed matter talk, but he takes the time to describe how little intervention really changed the way he and his students interact with each other and the relationship between them. I think it's a really nice thing for you to see. But people have tried it in many universities and benefited from it.
Thank you. Thank you. Yeah, please send that video. That sounds really interesting.
I will.
As well as your talk. One more question.
How has COVID affected learning in physics and learning in the classroom? Because I'm an undergrad and I know that it definitely had an effect, for sure. That's one way to put it, on how I learn physics.
So we recently wrote a paper for American Journal of Physics, which was based upon like our own experiences, so we basically gave written surveys to students, and we actually interviewed 37 students, 1 hour each, one-on-one, right? And one of the things that I would say to you, and these are, by the way, only for physics classes, students in physics classes. And one thing I would say that really stands out, is that the part that the students really loved was the interaction with the faculty who actually cared about them. So they said that even if the professor was talking to me only for like 1 minute and saying, how is everybody feeling? They were talking about their own adversity. They're like, oh, my kid is sick, or I was going through this, or my mom is going through this and I'm really concerned. I hope you all are doing well. I mean, this humanizing aspect, like even though it was like only for a minute, was so important for students that for those professors, they never wanted to miss their Zoom classes. They always showed up. They always were feeling like this is such a great community. They were feeling so supported and safe that they always wanted to come, even though it was a teeny tiny thing. Oh, is there anything that you wanted to discuss? Some people are showing their pets. And I know that, in your in-person classes, you cannot show this. But the interesting thing was that these 37 students that we interviewed, the thing that they really mentioned that they would like physics professors to do more in the future is, even in their in-person classes, if they try to be more human and like make those connections with the students, that would actually help. No, like, instead of going and just saying, okay, so we just finished Coulomb's law. Now Gauss's law states integral E dot dA is equal to Q enclosed over epsilon 0, and going on and on about the thing, and students are like, first of all, they are not even understanding why after Coulomb's law, like there's Gauss's law going on, what is the implication of all this, but also just like, making that personal connection, just going a few minutes early, making that connection in an in-person class would go a long way. This is one thing that the students were saying. There were a lot of other things too. Now, I don't know whether you were asking me about this aspect or something else, whether you were asking, has it negatively impacted students in K through 12 and other things so that, people actually are not necessarily ready for the next level, because that is another issue, right? I mean, like the other issue is that many of the K through 12 classrooms particularly were so negatively impacted that some of them completely shut down. Imagine how many years those students are behind, especially in their basic skills like math or reading, or writing. I mean, those are some of the skills that are the most important, so yes, physics is important too, but I'm just saying that in K through 12, you really want students to have that very strong mathematical basics, right? You want them to have like basic writing skills, and those things were completely gone. So I think that that is also another issue that is definitely going to affect people. I was reading somewhere, they were saying that the GDP will be affected, the world GDP, not the world, but in certain countries, they were saying, oh, the GDP will be affected by several percent going forward, just because of the fact that people who are impacted have not necessarily developed some of the skills. So yeah, that is a sad aspect, but you can read more about the things that we found in that American Journal of Physics paper, but this humanizing physics is really important because this aspect really stood out in individual interviews with 37 students and in the written surveys.
Thank you so much, Chandralekha. I think we better stop here. I want to
Well, thank you so much for having me. It was so
this was
great.
great. We will owe you. We're going to have wine and cheese now. We owe you a lunch or a dinner when you come to New York. I hope you'll come by and say hello in person when you visit. And thanks so much for this inspiring colloquium.
Well, thank you. Thanks for having me. Thanks a lot.
Bye-bye.